Assalamu alaikum, my children. This last video of the semester will deal with the theory of the ideal gases. We'll talk about the why and some of the implications for on the atomic level, and rather than the just vagaries of ideal gases, we'll try to dive into what it all means. Okay. So, the kinetic molecular theory of gases is the why to the explain the what is going on when we talk about the ideal theory of the ideal gas law. It was proposed by a gentleman by the name of Rudolf Clausius. You'll learn more about Clausius next semester when you hear about the Clausius-Clapeyron equation, and he deals a lot with kinetics. But he, at the age of 35, proposed this theory to explain why this all works. Some of these 5 premises we've already kind of heard and been understanding, but there are a few new ones. So, premise 1, that all gases contain a large number of molecules and or atoms, and they are in continuous random motion. That we need to understand that gases there's a lot of atoms and they're bouncing around. We need a lot of atoms so that we can get a good randomization and a good distribution of all of the properties. Now, the premise 2 is a total combined volume of all gases. If you shrunk them down and stacked them atom to atom, that volume is negligible in comparison to that of the volume in which they are contained. So essentially that gases have no real volume. Premise 3, that attraction and repulsive forces between gases are negligible. So the forces of sticking them together are so small that we can ignore them. That's not to say collisional forces don't play a part, but just attractive and repulsive forces. That's the other premise of the ideal gas law, that what makes an ideal gas ideal. Well, these last 2 are the ones that are really new. Energy can be transferred via collisions. However, the average kinetic energy of all molecules does not change with time. Only so the collisions are perfectly elastic, meaning that as they're bouncing around, some molecules speed up, some molecules slow down, but the net effect is the average speed of all the particles stays the same. They don't slow down over time. They don't speed up over time. They are more or less constant. Objects slow down because of a thing called friction or air resistance. That essentially objects are bumping into things to slow them down, but air is not bumping into anything. It is the thing that does the bump. It is the thing that slows down other things. But if you're looking at the, once again, system versus surroundings, if the system, instead of the air being the surroundings, if the air is the system, then it is not losing any energy. And the last premise is the average kinetic energy is directly proportional to the temperature in Kelvin, regardless of the gas type. So the only way to change the total amount of energy of motion is to increase the temperature. So with that in mind, you can think of our gases. Once again, pressure is collisions of fast-moving gas particles against the wall of a container. So Boyle's law states that at a constant temperature, so the average speed and energy is constant, there's an average number of collisions within a given frame of time in a certain volume. If you were to increase the volume, the gas will have to travel farther to hit the wall. So the rate of collisions per that unit of time would have to decrease, and thus the average pressure. Basically, if instead of a race that you have 100 laps and the 100 laps is around the block, if you say now each lap consists over a mile, you're going to get less laps per hour than if you leave it a block. Charles' law says that an increase in temperature means an increase in kinetic energy, so thus an increase in speed. At a higher energy, there should be more collisions and thus a higher pressure. That's our Gay-Lussac law that we didn't really talk about. However, if we want to keep the pressure to the same collisions, we need to increase the volume. Basically, a bicycle race doesn't need as much space as, say, a vehicular race. You increase the speeds, you need to increase the track size unless you want more collisions. More collisions may be what you're looking for. And the last one is Avogadro's law, that if we increase the sheer number of molecules, you would also increase the collisions unless you were to increase the volume. So just looking at that better helps us understand this. Well, looking at these, gases adopt a distribution of energies. They all have different speeds and thus different kinetic energies, because kinetic energy is 1/2 mass times velocity squared. Even though all the gases have different velocities, the average speed will fit a generalized distribution. This distribution looks at the number of molecules at a given speed. There you see at 500 meters per second, you have the most molecules at 300 Kelvin. Now you have some molecules that are moving almost zero, and you have some molecules moving almost 1,000. You even have a few that might be moving at 1,500. But generally speaking, we're working with the same amount of molecules. If you were to increase the temperature, you would see a shifting, redistribution of our atoms at various speeds. If you increase the temperature to 900 Kelvin, the average velocity jumps to about 1,000, where you have the most molecules. Now you still have some molecules moving at 500, some still moving close to zero, but now you have a good deal of them at 1,500, and some at 2,000, and some at 2,500, and even some almost at 30,000. Not 30,000, but 3,000. The average kinetic energy increases with relationship to that temperature. So there's actually a relationship that 3/2 R times T gives us our average kinetic energy. And if you're looking at the kinetic energy average per particle, you would just have to apply Avogadro's number in there. But these energy distributions can be described by what's called a root mean square speed, which is the velocity of a particle possessing the average kinetic energy of any gas sample of a known molar mass. That it's possible to convert this, the root mean square speed, squaring that, and we're finding what is the average velocity. It is a relationship that the velocity of the average molecule of gas is the square root of 3 times the gas constant times temperature over its molar mass. However, since the SI unit for velocity is meters per second, we have to do some clever calculation that we need to use a different R so it works out, and we have to use a slightly different molar mass. That in order to make this work out, you need, within that square root, you need meters squared per second squared. So we need to get rid of kilograms, we need to get rid of moles, we need to get rid of Kelvin. So we use the molar mass in kilograms per mole rather than in grams. And we use R in joules per mole Kelvin, which is kilograms meter squared per second squared mole Kelvin, rather than our bar or atmospheres. So that kilograms and kilograms cancel, moles and moles cancel, and Kelvin cancel, and we're left with meters squared per second squared. Now, we will rarely, if ever, use that equation as is. What is more useful is to compare properties of gases rather than looking at absolute speeds. That's where we get into two concepts, effusion and diffusion. Now, diffusion is the ability of a small concentrated volume of gas to expand and mix within a larger volume. That how fast, if you have a leak, will this gas spread and become uniform throughout the air? If someone drops tear gas into a room, how long does it take for that tear gas pumping out the gas to fill the room so that no place is safe? Now, this depends on two factors. All of these will depend on the root mean square velocity, but it will also depend on what's called the mean free path. It's basically how much gas is currently in the room. Because if there's a lot of molecules of gas, the new molecules have to elbow their way through to get through. And so there's a lot of ricocheting and bouncing and redirecting, and the gas molecules take a while to get through. However, mean free path is hard to calculate, and there's not a good formula for this, so we will not deal largely with diffusion. Effusion is a lot easier. Effusion is the expansion of gas through a small hole based on pressure differentials. You have a low pressure system on one side and a high pressure on the other. How long will it take the gas to equilibrate? That same tear gas example, how long will it take for that tear gas to fully empty itself? Not how long will it take to fill the room, but how long will it take for it to empty itself when compared to other gases. Because there's a pressure differential, the effusion rate only depends on root mean square velocity. We're looking at a high pressure container up here where gas is bouncing around, and what's the likelihood of the gas molecule hitting a hole and popping through? So we get what's called Graham's Law of Effusion. Graham's Law of Effusion says the relative rates of effusion of two gases are directly related to the square roots of their molar masses. And that's because since effusion only depends on root mean square velocity, if I'm comparing two gases at the same temperature, you got 3 RT over mm. Well, 3 RTs cancel out, and you're left with only mm1 and mm2. Now, this explains why helium balloons should go flat faster than air balloons. Because if you look at this chart up here, krypton is a heavier gas. So because it's heavier, it can move slower and still hit as hard as the lighter gases. Oxygen and nitrogen are lighter, and so they need to be moving faster to hit the same amount of energy. Helium is even lighter, so it has to move faster. And hydrogen, being the lightest gas, it would be moving the fastest, because if I fill up air, it's mostly nitrogen, so it's going to be moving slower. The likelihood of slow-moving gas hitting that hole is a lot less than the likelihood of a fast-moving gas hitting that hole. So this problem right here is going to be dealing with that. At 100 degrees C, what is the root mean square velocity of steam, of water essentially, and how much faster will it effuse with respect to oxygen? Okay, so let's look at this. We're almost done with our document camera. Temperature 100 degrees C. Add 273 to make it 373 Kelvin. Okay. The velocity is equal to the square root of 3 times 8.314. That's kilograms, meters squared, second squared, mole, Kelvin. And a temperature of 373 Kelvin. And on the bottom, our molar mass. Molar mass of water is 18 grams per mole, so that means it would be 0.018 kilograms per mole. Per mole, kilograms, Kelvin, Kelvin. So all that, I'm going to do all of this inside the square root before I calculate it. 3.8.314 times 373 divided by 0.018. So this is going to be a big number. It's equal to the square root of 516,853.6 meters squared, second squared. And I square root that. And I get the root mean square velocity is 718.9 meters per second. Which technically, let's see, 5,000, but then multiply by 60, means it's moving something like 2,588 kilometers an hour, if I'm just allowing it to bounce around. Okay, that one's a little silly. But if I want to compare the rate, what is the rate of water compared to the rate of oxygen? Now here's the trick. We look at the molar mass of oxygen over the molar mass of water. 1 O is 16, so 2 O's is 32. Do I need to use kilograms? No, because grams per mole over grams per mole cancel out. The square root of 32 over 18 is 1.3 repeating. Now, if done right, this should always give you a number that is greater than 1. 1 would mean it is the same speed. The same speed, but this means it's moving 1 1/3 times as fast as the oxygen would. It would escape 1 1/3 times as fast because of that. Should always be looking for a number that's greater than 1. Now, the last little bit has to do with real gases. Real gases are, this stuff is for engineers, people who are smart, who need to deal with real world situations. For an ideal gas, we assume that the molecule has no volume and no attractive forces. And this works very well at low pressures. But at pressures above 10 atmospheres, we start to see a serious deviation from an ideal gas behavior. That essentially, here's a gas trying to hit that wall and create a collision. If there's an attractive force pulling this, it's holding it back and it's going to hit a little bit softer. If the gases are taking up a little bit of space because of the volume, that means there's less room for them to jostle around, and so the volume effect. So gases will deviate based on the element and with the decreasing temperature. So as a gas starts to condense, it will begin to become less and less like an ideal gas. If all gases were ideal, we would not have liquid water on Earth. So with that in mind, we're considering all these things. So besides just the size, we will consider what we call the intermolecular attractive forces, known as van der Waals force. Now, we will learn the individual forces later on, but for now, we'll just look at them as one big thing as van der Waals. Now, as we see here, at different temperatures, how does it differ? At low temperatures, high pressure, you see a serious deviation. And then as we increase the pressure higher and higher and higher, so it's dropping. It's saying essentially as pressure is low but still moderately high, that it's more compressible, but then at higher pressures it becomes it's changing properties. Sorry, and then at 500, you see greater it's like almost a less of a deviation. At 1,000, it's always above the line, because at 1,000 Kelvin, the gases are not likely to condense. It still means the pressure is actually higher than what you would expect, but it's not condensing. So below the line means the pressure is lower than you would expect at that pressure. And so, or the volume is lower than you would expect at that pressure and temperature. So, now, this equation was discovered by Johannes van der Waals, and it's essentially the sum of all the attractive and repulsive forces that, I said, we won't learn the names yet, but he's able to make an equation that essentially accounts for this. So notice, instead of PV equals nRT, and now it's P plus n squared A over V squared times V minus NB all over equals to nRT. The A n over V squared term corrects for any attractive forces that's going to affect the pressure. The negative NB corrects for the actual volume of the gases, the moles of the gas times the size of the gas. Why this is n squared over V means that if there's a bigger volume, even if you have more atoms, the gases have to travel farther to interact. But if there's more moles of gas, there's going to be more interactions, and A is the interaction force. Now, A and B are constants, and they will vary from gas to gas. If we were ever to run an equation with this, we don't need to know them. They would always be given. Just like you learn the enthalpy of reaction temperatures from a chart, you would learn these A and B values from a chart. We don't need to memorize those. You just would need to know how to use them. So this very, very last equation is by what temperature would the temperature deviate for CO2 if from ideal gas if our pressure was 12 atmospheres, volume of 3 liters, and our A is 3.59 and our B is 0.0427. So this very, very last one we're going to use our dot cam for, and that's where we're going to leave it. So PV over NR equals T. So what is our ideal situation? Our ideal situation has 12 atmospheres, 3 liters, 2 moles, and a gas constant of 0.8206 atmosphere, liter, mole, Kelvin. So 12 times 3 divided by 2 divided by our R, 8206. So at a ideal situation, you would have 219.4 Kelvin. Or essentially, under ideal pressure conditions, it'd be something like negative 53 degrees Celsius. Very cold, very cold. Well, under non-ideal, 12 plus 3.59 2 squared over 3 squared, and then 3 minus 2 times 0.427. And then we're going to divide that by then N and R, 2 and 0.8206. So I'm going to find each of those terms separately. So our actual pressure or effective pressure is, our effective pressure is closer to 13.595. For God's sake. Really? So 13.595. Our effective volume is 2.9146. So 13.595 and 2.9146 divided by our moles divided by our R puts our temperature somewhere at 241.43. Well, if I correct that for Kelvin, so it's changed from negative 53.6 to negative 31.6. That's not an insignificant amount. Not an insignificant amount. Especially, this is not even that much gas. If I had much more gas, it would play a much bigger part. So, and this is only at 12 atmospheres. So much higher pressure, we're going to see much more deviation. And so it's just noting that we see a direct deviation even under these conditions. But that is the limit of what we will cover. And so hopefully you found this helpful as a way to study these concepts without having to review these in just a plain digital form. You now have a video form of all these chapters. Have a good rest of the day.